Hello, welcome to another section in further mathematics. Today we'll be talking on differentiation using first principle. But before that, let us review our previous lesson. Okay, welcome back. When I'm talking about differentiation in further mathematics simply means the rate of change. It simply means the rate of change. That is, you're talking about how a particular substance changes with respect to time. So when you're talking about differentiation using first principle, there are steps needed in actualizing those things, and the steps are 5 in number. So the 5 steps in first principle, the 5 basic steps in first principle include: number 1, that is fx, which is usually given. The second point here is fx plus h, where h is equal to change in fx. Number 3, fx plus h minus fx. Number 4, fx plus change in h minus the fx. Then number 5, lim as x tends to 0 of fx plus change in h minus fx all over change in x if it exists. Now these are the 5 basic rules needed in dealing with differentiation using the first principle. So with these steps being taken into consideration, we can solve every equation given to us using first principle. I definitely want us to apply the concept, and see what we will definitely get. So we are trying to definitely apply the 5 steps in seeing what we'll get in this differentiation. For example, differentiate fx equals to x squared. Now you apply the first step, you convert fx to y. Let's call it y. Let f of x be equals y. So the equation becomes y equals to x squared. But remember, we are talking of change, so let's add it. Y plus, this is y plus change in y is equals x plus change in x. Remember, our x has a square sign on top of it. So you now have y plus change in y equals, let's expand this. Now let's just do a rough sketch of, let's do the expansion somewhere here. You have x plus change in x plus change in x. So we now have x times x is x squared. X times this is, that is plus x change in x. This times this plus change in x plus x times this give you change in x all square. Remember, this is just an explanation. So you now have x square plus, this is x dx, that is plus 2x dx, then plus change in x square, this is change in x, plus 2x change in x, then plus x square. So this is what we get. So this becomes x square plus 2x dx plus change in x all square. Now we are dealing with change in y. Let this y go this way. We have change in y is equals x square plus 2x change in x plus change in x all squared minus y. But remember, when we started, y was equal to what? And y was equal to x square. So we now have change in y will be equal to x square plus 2x dx plus dx all square minus, in place of y we put what? Look at our y is equals to x square. We now put x square. Now according to the rule, this is x square, this is minus x square. X square goes with minus x square. We now have this change in y is equal to x dx plus change in x all squared. Then we divide all two by change in x. Divide here by change in x, and this one you divide here by change in x. So you're dividing all through by change in x. So you now have this change in x goes with this, and so the change in y is on dy dx as lim x turns to 0. So we now have this to be equal to x plus, if you differentiate x squared, you have your value will be equal to 2x. Now I want us to try another question. Let me say if we have a question like, let's do our board this way. Let's say you're being told to differentiate. Okay, differentiate y equals x3. Now at this point we'll definitely apply the Pascal triangle. So we now have the same rule we used in the last days. We have y plus change in y is equal to x plus change in x raised to power 3. And you know, change in x raised to power 3 according to Pascal triangle, when we have 1 1 2 1 1 3 3 1. So this will be our number. So we now have y plus change in y is equals x raised to power 3, this is for this, plus 3x change in x for this 3, plus 3x change in x, this is for this. Then the last one now will now be the change in y, change in x plus change in x. But remember, it's raised to power 3, so this is 3 and this is 2, y this is 1. So the plus sign here, this is 2 and this is 1, this is 3, this is 2 and this is 1. So we've expanded this x plus this raised to power 3 using Pascal's triangle. This is Pascal's triangle. Pascal's triangle. I know we did this in our previous section, how to expand numbers as large as 4, 5, 6 using the Pascal triangle. Now with this, we now bring down change in y is equal x3 plus 3x squared change in x plus 3x change in x all squared cube minus, now at this point what we are having here now is where is our number? okay, minus y, but in place of y we are putting x cubed, just like what we did in our previous listing. So we now have x3 is living with x3, so changing y becomes equals 3x square changing x plus 3x changing x all square plus changing x cube. Now we are dividing with changing x because it's rate of change. This is changing x, and we are dividing this by changing x. So this cancels 2, this becomes 2, this goes with this, we have 1, and this takes off this. Dy dx, as the x tends to 0, we now have 3x squared plus 3x 0, dx tends to 0, plus 0 raised to power 2. So this becomes 3x squared. This is 0 plus 0 plus 0. So we now have dy dx to be equal to 3x squared. Now this is it for first principle. So if y is equals x cubed, then dy dx is equal to 3x squared. Now with this, I know you can handle any question that comes up in differentiation using first principle, but there is a rule that is guiding all this. So I would like us to go into proving it, and at this point we will need to employ the services of the binomial theorem in proving it. So if y equal to x raised to power n, find dy dx. Now let's go into proving this point. Remember our normal rule, y plus change in y is equal to x plus change in x raised to power n. We now have y plus change in y. According to binomial, expanding this, you now have x raised to power n plus combination this 1, x to the power n minus 1 x plus n combination 2, x to the power n minus 2 this x square plus to plus changing x plus changing x raised to power n. Now this can be broken down into x raised to power n plus, this is the same thing as n combination 1 is n s to the power n minus 1 plus, okay, n raised to the power n minus 1 change in x plus, here is n minus 1 all over 2 factorial, here is 1 factorial, change in x square plus this raised to power n. Now we now have change in y is equals, these are value x raised to power n plus n x n minus 1 dx all over 1 factorial plus n minus 1 all over 2 factorial changing x all square plus dot nx raised to power n, there minus our y is what? X raised to power n. So that this x raised to power n cancels x raised to power n. We now have change in y to be equal to n x to the power n minus 1 change in x plus n minus 1 all over 2 factorial change in x raised to the power 2 plus until you get to x raised to the power n. Then let's divide all through by changing x, and we divide this by changing x, divide this by changing x, and divide this by changing x. So this goes with this goes with this, and this still goes with this n. So we now have dy dx as dx tends to 0 is equals, we now have n minus 1, then we now have plus n minus 1 times 0 over 2 factorial plus dot dot plus 0, because the n is 0 raised to power n, which is equal to nx n minus 1 plus 0 times everything here is 0 plus 0 times everything here is 0. So our final answer is nxn minus 1. So dy dx is equal to this. So therefore, for if y is equal to x to the power n, then dy dx is equals nxn minus 1. So this happens to be the standard of solving every differential equation. We'll apply this formula in solving every differential equation from now henceforth, in as much as it has to do with accurate differentiation. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen. Do well to always use the lesson notes on the platform for a better information on the topic we've discussed. Always feel free to drop your questions on the comment section. We'll be so glad to have a question come up. So thank you. See you in our next class.